Hello students, welcome to the EduSat classes on Automata Theory and Computability. Automata Theory and Computability is a 5th semester core subject for both computer science and information science students. So, first module it has been covered by Professor Kodanpur sir. I will be covering the second module. So, before starting, let me introduce myself. Myself, Dr. Girijamma H.A., professor working in the Department of Computer Science and Engineering, RNS Institute of Technology, Bangalore. So, I have taken this subject more than 15 times for both UG and PG students, and I have done my research in this area. So, if you have any queries, so you can freely contact to the mail ID which is displayed here. Okay, it is girijasal@gmail.com. So, before starting my session, I want to thank the special officer and the VTU EduSat team for giving me an opportunity to share my knowledge. I tried my level best to help the students in a better way. So, let us start the session. So, first, books to be followed. Books to be followed are Alan Rich, which is the author of the book Automata, Computability and Complexity. So, I say students, this is a very good book, as in the earlier we used to refer, only staff used to refer the textbook, but this is student friendly and it is commonly described in common English and easily understandable by students. Next book is KLP Mishra and N. Chandrasekharan. So, this is we will be referring here for the 4th and 5th module, and all the reference books listed in the syllabus will be covered. So, let us go through the syllabus of module 2. So, module 2 is basically on the regular expressions. So, regular expressions, it is from the Alan Rich first textbook from chapter 6 to 8 from Rich book. So, first regular expressions is clearly explained in chapter 6, and regular grammars is explained in chapter 7, and regular and non-regular languages, they are defined in chapter 8, that is from the sections 8.1 to 8.4. So, today's topics for discussions are, so what is a regular expression? Basically here we will be defining the regular expression. Next we will be defining the semantic interpretation function L for the language of regular expressions. Next, analyzing a simple regular expression, what language it accepts, that we will analyze it. Next is finding an RE for the given language. Next, operators of regular expression. Next, Kleen's theorem. Okay. So, there are two parts of the Kleen's theorem. So, we will be proving both the theorem, both the statements. Next is building an finite state machine from a regular expression. So, next I will be discussing the examples. So, today's topics, so I will be starting with the module 2, starting with regular expression. So, let us see what is a regular expression. So, regular expression, it is nothing but a string or a pattern that we will be using in our daily routine. For example, if you want to search in a web, okay, so we will be supplying the string. That string is nothing but the regular expression, and similarly in your email box, spam mails are sorted by looking into the regular expression. So, basically I will be discussing all these applications in the applications of regular expressions. Okay. So, for time being, regular expressions, they are nothing but another way of defining the languages. So, in the module 1, so we have seen that regular finite state machines accept the languages. So, when they will accept, so if they reach the final state, so we say that that finite state machine accepts the language. Similarly, another way of defining the language is through regular expression. So, regular expression, it is a string that can be formed according to the some rules. Okay. So, some rules are there. So, accordingly you need to write the regular expression. So, let us see what are all those rules. First rule is phi is a regular expression. What is phi? phi is a empty language. So in the first module we have seen the finite state machines for some language will define phi. Phi means when there is no transition will define phi. Similarly here phi is a regular expression. Second rule is that epsilon is a regular expression. So what is epsilon? Epsilon is a null string. So it is also a regular expression. Next, coming to the third rule, every element in sigma is a regular expression. For example, so you know that sigma is defined on symbols. It may be A, B, 0, 1 like that. For example, if you consider sigma as AB, so every element, that is A and B, it is a regular expression. Next, given two regular expressions alpha and beta, if you perform the concatenation, that is alpha followed by beta, it is a regular expression. Okay. So these regular expressions, these are the preliminary or the basic regular expressions we will be defining. Next we have the fifth rule. So what is that fifth rule states is, given two regular expressions alpha and beta, so if you perform the union, that is alpha union beta is a regular expression. Next, given a regular expression alpha, alpha star. So alpha star is also called as clean closure or star closure. So it is clean because it is named after a person Stephen Kleene. Okay. So it is a regular expression. So what is alpha star? Alpha star means 0 or more number of times repetition. Okay. So I repeat here. So alpha star, star means 0 or more number of times this alpha can be repeated. So that is, if you perform a star operation on alpha, again the resultant will be a regular expression. Seventh rule is, given a regular expression alpha, alpha plus is a regular expression. What do you mean by alpha plus? Alpha plus means one or more times alpha is repeated. Okay. So I repeat here, alpha star is 0 or more number of times repetition, whereas alpha plus is one or more times of repetition. So while writing the regular expression, if you need one time compulsory, then you can use plus. Okay. So if you need 0 or more number of occurrences, then you can use star. Next, given a regular expression alpha, if you write in parenthesis alpha, it is also a regular expression. Now, so using these rules, so you can form the regular expression. For example, if sigma equals AB, the following strings are regular expressions. So what are the strings? For example, phi is a regular expression, epsilon is a regular expression, and the input symbol A, which is taken from the input alphabet A, it is a regular expression. Then B, it is a regular expression. Then if you perform the union, that is A union B, okay, it is also a regular expression. And if you write in parenthesis, again it is a regular expression. If you perform whole star, okay, it is a regular expression. So now what does this mean? A union B whole star. It means that either you can take A or B and it can be repeated 0 or more number of times. Okay. So simply ordinarily we say the languages contain A and B, strings contain A and B. So that can be written as A union B whole star. In some of the earlier textbook, instead of union they have used plus, even that is correct. So in the prescribed textbook, Align Rich book, so the author had made use of union. And similarly, when you perform the concatenation, that is A followed by B followed by B followed by A union epsilon is a regular expression. So I repeat, in regular expression we use three operators, mainly union, concatenation and star closure. Apart from this, alpha will be regular, phi will be regular expression, epsilon will be regular expression. Okay. So let us see the semantic interpretation function L for the language of regular expressions. Okay. So now we have defined the rules. So those rules, suppose phi is the language, what will be L of phi? what will be the language? Okay. So, the language of phi is nothing but phi, the language that contains no strings. For each rules whatever we have defined, we will define the L of epsilon or whatever it may be the regular expression. Now, L of epsilon is nothing but epsilon, that is the language that contains empty string. Next, third semantic interpretation is for any C which belongs to sigma, L of C is C, that is single input symbol C, it is the language that contains single character string C. And similarly, for any regular expression alpha and beta, so if you perform the concatenation, for example, L of alpha beta, it is nothing but L of alpha followed by L of beta. Next, for any regular expressions alpha and beta, so if you perform the union, that is L of alpha union beta is L of alpha union L of beta. And similarly, for any regular expression alpha, so what is alpha star? L of alpha star is nothing but L of alpha whole star. Okay. So, that means if you want to write the language of an like for example A star, so we will simply write A star. Okay. So, like that you can use the semantic interpretation. And for any regular expression alpha plus, okay, so L of alpha plus, it can be written as I said you, plus means it is one or more times repetition. So, it can be written as L of alpha followed by alpha star. Why we have to write like this is alpha is one time, it is compulsory. Next, alpha star is 0 or more number of times repetition. So, for alpha plus, so we will be following alpha alpha star. So, this is nothing but L of alpha followed by L of alpha whole star. Next, lastly, for any regular expression alpha, so L of alpha within parenthesis if you write, it is nothing but L of alpha. Okay. So, next let us analyze a simple regular expression. For example, if you want to analyze L of A union B whole star followed by B. Okay. So, if you observe here first we are performing the concatenation. Okay. So, this is L of A union B whole star followed by L of B. So, it is L of A union B whole star followed by L of B. So, this L of A union B, it can be written as L of A union L of B whole star followed by L of B. Okay. So, this is nothing but L of A is nothing but the single character string that we can write it as A in flower brackets. Okay. So, similarly B. So, it is A union B whole star followed by B. Okay. So, what does this specify? Okay. So, A union B whole star B is the set of all strings over the alphabet A and B that end in B. So, why do we write like this? Because so here starting you can have A or B 0 or more number of times repetition. Okay. So, whenever you have star, it indicates that 0 or one more number of times this can be repeated. So, starting when union we will use for either or, either A or B. Okay. So, here starting you can have the strings of A or B and this can be repeated any number of times. At the end of the string B is compulsory. Why B is compulsory? Because the language is defined like that. Okay. So, depending on the language whatever it is given, so we will be writing the regular expression. So, we will consider another simple regular expression. So, it is L of A union B followed by A union B followed by A and A union B whole star. Okay. So, what do we observe here? Here these two are options, starting two individual letters you can have either A or B followed by A, okay, that is compulsory, third letter A is compulsory, and after that you can have either A or B any number of times. So, that only it can be written as L of A union B followed by A union B, followed by L of A, followed by L of A union B whole star. So, the same thing, so it is expanded and it is written. So, finally, so you will be having A union B followed by A union B followed by A followed by A union B whole star. So, what language it describes? So, it describes the all the strings, they are in the form of XAY. Okay. So, X is any X and Y are any strings of A's and B's, and the length of the string X, that is, it is given as mod 2. That means, here starting 2 letters or starting 2 symbols. So, you can have either A or B, whereas third one is A is compulsory followed by Y. Y can be of any length, it can be 0 also. Okay. So, the strings, they will be in the form of XAY. So, X and Y are strings of A's and B's, and length of the string X is mod 2. So, that is why the regular expression will be A union B followed by A union B followed by A, then followed by A union B whole star. Next, let us move to the finding the regular expression for a given language. So, here you have to stress more. Why? Because in the final exam, there will be 2 to 4 questions, they will be giving the language and they will be asking you to write the regular expression. Okay. So, it comes by practice. So, first let me consider some simple language. Okay. So, I am defining the language L as W, which belongs to AB star. That means, W is a string which belongs to the input alphabet AB star, such that W length of the W is E1. Okay. So, what do you understand here? That means, here you should write the regular expression for the strings of E1 length. Okay. So, my suggestion, students, before writing the regular expression, write some sample strings which are accepted by this language. Okay. So, if you write, for example, it can be either AA, AB and AB, BA, however you form, but here the string length is important. The string length is E1. So, mod of W, that means the length of the W is E1. Okay. So, if you observe whatever the strings have written, it is of 2, 4, 6, 8, etc. like that, it continues. So, once you write some strings, so you will get an idea to write the regular expression. So, this part is very important from the exam point of view. So, how do we write the regular expression? So, here A union B, either starting, it can be either A or B followed by A or B, and these two are compulsory and this can be repeated any number of times. Okay. So, that means, so either it will be first starting it will be 2, 4, 6, 8 like that. Okay. So, here this regular expression, it will not accept the strings of odd length. Okay. So, if you observe, so or else in a combination only 2 letters are there. So, you can write AA, AB, BA, BB. So, even this way also you can write the regular expression. Okay. So, first step is write some sample string. Let us move to the second one. Second example is L equals W, which belongs to AB star, and W starting with the string ABB. So, what does it define here? Here it should accept the strings of W which start with ABB. ABB is compulsory, and afterwards it can have either A or B any number of times. Okay. So, if you write the sample string, it will be starting minimum ABB, then ABBA, then ABBB, ABBAB, like that anything you can write. So, if you observe here, starting in all the strings ABB is there. So, the regular expression will be ABB is compulsory, A concatenated with B followed with again concatenated with B followed by A union B whole star. Okay. So, this is starting with ABB. Let us move to the further examples. Okay. So, let me take another example. So, here W which belongs to AB star. So W ending with string ABB. Okay, so here L equals ending with ABB means, so my string may end with only ABB, and starting it can have either A then ABB or B ABB or AB ABB, like that it can be anything. But here one thing note important is, starting it can have anything, but ending ABB is compulsory. So we write the regular expression as A union B whole star followed by ABB. This is compulsory, since ABB is compulsory at the end. Okay. So depending on the language, what the given language, the regular expression changes. Let us move to the fourth example. So fourth example is strings W which belongs to 0, 1 star. Okay. So instead of A and B, I have taken 0 and 1. Okay, where W have 0, 0, 1 as a substring. So what do you mean by substring? Substring, it can occur in the main string anywhere else. Okay, either starting or ending or in the middle. Okay, so here see, only 0, 0, 1 can be there, or here, or in the middle, and before and after it can be anything. Okay, so when you write some sample string, so you will have the idea of writing the regular expression. Okay, so the regular expression will be, so starting it can be anything, 0 union 1 whole star followed by 0, 0, 1. Okay, so this is compulsory because the given language contains 0, 0, 1 as a substring followed by 0 union 1 whole star. Okay, so next let us move to the fifth example, where here W does not have 0, 0, 1 as a substring. Okay, so here we wrote 0, 0, 1 as a substring. Here we should write 0, 0, 1 does not, W does not contain. Okay, so whenever you want the complement in the module 1, so we used to change the accepting state and non-accepting state. Okay, so but here you cannot do like that. So you should rewrite the separate regular expression. For example, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1. So you can write like this, which do not contain 0, 0, 1 as a substring. So what you observe here? Okay, so here you in the regular expression while writing, here you cannot take 0. If you take 0, so next time again you can have 0. Okay, so in order to avoid that, so we can write 1 union 0, 1 whole star. Okay, so if you write like this, so you cannot have a chance of 0, 0, 1. Okay, so first starting you can have 1. Okay, then or 0, 1. Okay, so if you want here 0, this is whole things, this thing will be 0 and 0. 1 means only 1 will be there, and 0, 1, 0. Okay, so 0, 1 here from this and 0 from this. Next 1, 1, 0. Okay, so 1, next 1, next 0, next 1, 0, 1. Okay, so 1 first time, next 0, 1, and this is 0 number of times repetition. Okay, so like this, if you write the regular expression, you can avoid the 0, 0, 1. Okay, for the first time this will not come. Once you practice writing many languages, it comes to you. So only I have discussed more examples on writing the regular expressions. So next let us move to the sixth example. So sixth example is, it contains the strings W which belongs to AB star, and W contains an odd number of A's. So what does it mean? That means, so your strings should contain odd number of A's. He is not worried about B's. Okay, so he is not worried about the position also. Only thing is, whenever you write the strings, A number, that means number of A's in the string should be of odd. That means they can be single A, 3, 5, 7, 9, like that. Okay, so for example, single A, 3 A's. So if you observe here, AB, ABA, here 3 A's are there, B's are 2. We are not worried about the number of B's. So we are worried about only the number of A's. Okay, so for example, if you take this string, it is BB then 4 A's followed by single B, then again B. Okay. So, here there are 3 B's and 5 A's. Of course, this should be accepted. So, whenever you write the regular expression, it should the regular expression should not accept the wrong strings, like how in the module 1 we have designed the finite state machines, so that if you accept the wrong strings, it will not enter into the final or accepting state. In a similar way, so your regular expression, whatever you write it, it should not accept the wrong strings. It should accept only the correct string. So, one way is either, so if you observe here, starting it can be either A or B. So, I will write B star, then followed by A, followed by B star, again A, followed by B star. These two A's, why I am not giving star here is because this will generate an even number of A's. Okay. So, B's it can be anything, that is why I have given star here. For A we have not given star. Why? Because this will generate an even number of A's, followed by single A will generate the odd number. Okay. Again followed by B star, so it can be anything. So, your regular expression becomes B star followed by AB star whole star followed by AB star. Either you can write like this, or another way is B star followed by AB star. That means here we are, whatever we are writing, here first we are writing that, followed by this will generate a even number of A's. Okay. So, that you can write it afterwards. So, you can write either this way or this way, both are correct. Next, let us move to the another example, where here W contains the strings of which belongs to AB, such that hash A of W, that means number of A's in a W mod 3. Mod 3 will be normally will be using for the to find the remainder. Remainder is 0, means you should generate the strings which are multiples of 3. So, that means whenever you divide the length of the string by 3, the remainder should be 0. The meaning of this is, okay. So, either they can be length of 3, 6, 9, 12 like that. Okay. So, here what you have to generate is, you have to generate strings which contains the length in the multiples of 3. Okay. So, here in a similar way, in the previous whatever we have done, here A, you can define whole together, and then for that, so you can give star. So, star means this can be repeated 0 or more number of times. Okay. So, one time means 1, 2, 3 A's you will be having, next you will be having 6 A's, next you will be having 9. So, like that, followed by B star. Okay. So, after each A we have given B, because B can occur anywhere else. So, other than this, if you observe here, so it accepts the strings of which are multiples of 3 only. Okay. So, other than that it will not accept. Here not only, here only the number of A's is important. Okay. So, we are not considering both A and B. If you are considering both A and B, then this expression will be different. Now, let us write the regular expression for the strings which contains A and B which of length less than or equal to 3. That means number of A's in a string is less than or equal to 3. Maximum is, it can be 0, that is epsilon, or 1A, 2A, 3A. So, more than 3 A's it should not contain. So, the regular expression will be, suppose for example single A, 2A, then 3 A's, and these A's can occur anywhere else. So, you can write the regular expression like this, B star, then followed by single A means it can be epsilon. Okay. So, you can be A followed by A or epsilon, next followed by A or epsilon, followed by A or epsilon. Only 3 times we are writing, because here it is less than or equal to 3. Okay. So, in between B's it can have. Okay. For example, here if it is 4, next one more times you should write A union epsilon. Okay. So, this like this, even you can generate the string, you can write the regular expression, so which are less than 3 also. Next, let us move to the 9th example. Okay. So, here the language is defined on zeros and ones. It contains the strings of W and with no consecutive zeros. Okay. So, no consecutive zeros means it can be 0 or epsilon or 1, 0, 1, 1, 0, 1, 0, 1, 0 can be there, but 1, 0, 0, 1 cannot be there. That means two continuous zeros it cannot have. It can have 1, 1, 0, 1, 0, 1. Okay. So, it can be, to generate these two, we write specifically either 0 or epsilon followed by 1 union 1, 0. Why? So, if you take any combination, it will not generate continuous zeros, because if I write here 0, then here 1, 0. So, 1, 0 next 0, it will be continuous. So, in order to avoid that, you should write the regular expression 1 union 1, 0. Okay. So, this is the regular expression for right, and sorry, here it is 1 union 1, 0 whole star should be there. Okay. So, next is W, which belongs to 0, 1 star, and W contains at least 2 zeros. Okay. So, here in the previous example, he quoted that it should not contain 2 consecutive zeros, and here he is describing at least 2 zeros are compulsory. So, how do we define it? So, minimum it can have 2 zeros, or it can have 1, 0, 1, 0 or 1, 1, 0, 0 or 0, 0, 3 zeros it can have. At least means that is 2 zeros compulsory. So, starting it can be 0 union 1 whole star followed by 0, followed by 0 union 1 whole star, next followed by 0, followed with 0 union whole star. See, if you observe here, I have made here 2 zeros compulsory. Suppose if it is 3 zeros, next one more 0 we should write, and you should extend that. Okay. So, likewise, regular expression writing depends upon the what language is given. So, next let us move to the different types of examples. Okay. So, here strings are of type a power n, b power m, such that n is greater than 4 and m is less than or equal to 3. Okay. So, that means, so your regular expression will be, so 4 a is compulsory followed by a star. Okay. Here you observe it defines the language which contains n number of a's followed by m number of b's. That means, so first you should have a's only, then you can have b. You cannot have like the previous examples a b like that. First it should contain a, and what is that length of the a? N is greater than or equal to 4. So, first 4 a is compulsory followed with a star. That means, afterwards it can have still more number of a's followed by b's. So, b's can be less than or equal to 3. So, we write either epsilon or b or bb or triple b. Okay. So, this is the regular expression which for this given language. Next, let us take one more different example, that is a power n, b power n, where n is less than or equal to 4 and m is greater than or equal to 2. So, the ulta way we should write it. The previous example whatever we have written it, so it is for b whatever we wrote, here similarly we should write it for a followed with b, b, b star. Okay. So, here this 2 is compulsory followed with b star. Next, a power, the next example is a power 2n, b power 2m, okay, where n is greater than or equal to 0 and m is greater than or equal to 0. Okay. So, here if you observe, they are nothing but the multiples of 2. Okay. So, that means even number of a's followed by even number of b's, because here in both the powers, so you have 2, 2. So, easily you can write the regular expression as a whole star followed with bb whole star. So, this will generate even number of a's and this will generate even number of b's. Okay. So, the last example is 8 power n, b power m, such that m plus n is even. Okay. So, now the whole m plus is even when both a's and b's are even or both odd. Okay. So, for that you can write the regular expression like this. Okay. So, here both this when you add the powers of A's and B's, it should be even. So this will happen in maths only when both are even or both are odd. Okay. So this is the regular expression to write the even number of A's and B's, and this is to generate the odd number, that is single A followed by AA whole star followed with single B, BB star. Okay. So this is the regular expression. So far we have discussed the so many examples. So others I will be discussing in the e-notes provided to the VTU. Next, let us move to the further topics. Okay. So we have observed that three operators we have used in the regular expression. So let us see how they can be used in precedence. That means, so precedence comes to a fact whenever you want to evaluate the regular expression. Evaluation is nothing but which operation should be considered. So first, clean star or star closure, it is having the highest precedence. Next comes the concatenation, next comes the union. For example, if you have A union B, B star A, it is first B star is evaluated. You cannot take A union B. Why? Because star is having higher precedence. Okay. So star is having higher precedence. So first B star will be evaluated followed with concatenation. That means first B star, next B concatenated with B star followed by A. Next you will be performing the union. Next, so we will move to the Clean's theorem. Clean's theorem, which is very important in defining. So here there are two parts. So what does the theorem 1 says? Any language that can be defined by a regular expression can be accepted by some finite state machine. That means any language, okay. So if you have a regular expression, you can construct the finite state machine. So theorem 1, so we will be proving in this today's session, and further theorem 2 is the reverse of this. That means any language that can be accepted by a finite state machine can be defined by some regular expressions. So this I will be taking in the next lecture. Okay. So we will be proving the theorem 1. So theorem 1, what does it says? For every regular expression there exists a finite state machine. Theorem 2 states that for every finite state machine there exists a regular expression. So let us move to the theorem 1. So building an FSM from a RE. Okay. So how to build a finite state machine from a regular expression? So normally we will be building a non-deterministic finite state machine from a regular expression. Okay. So that is the Clean's theorem first part. That is theorem 1 states that for every regular expression there is an equivalent finite state machine. The proof is by construction. We construct the preliminaries and then we will move further. Okay. So first we will consider that if the regular expression is alpha, then we can construct a finite state machine. FSM stands for finite state machine M, such that L of alpha is L of M. Okay. So here if alpha is any C, if contains C, then there will be a start state and one final state. This is the figure. Next, if alpha is any phi, okay, there will be no final state. So we construct the FSM as shown in the figure. And if alpha is epsilon, then we construct a simple finite state machine as shown in the figure. Only there will be a final state which accept epsilon. This is for phi and this is for epsilon. Next, we will consider beta and gamma be two regular expressions such that L of beta is regular. Okay. So L of regular, if it is regular, then it should be accepted by some finite state machine M1, which is defined with K1. These are the number of states. Sigma is the input alphabet. Delta is the transition function which is defined from state and taking the input to another state, and S1 is the starting state and A1 is the accepting state. Okay. So this is for L of beta. Similarly for L of gamma, so we have a finite state machine M2 which is defined with K2, sigma, delta 2, S2 and A2. suppose if you want to perform the union, as we all know that, so only thing is you can perform with regular expression is either union or concatenation or star closure. Okay. So if you want to perform the union, that means L of M3 is given with L of alpha, and which is nothing but L of beta union L of gamma. So we'll add a, this is beta, this is gamma, we add a one more starting S3 with making epsilon transitions to S1 and S2. So here alpha is given by beta union gamma. Okay. So beta is one regular expression which is accepted by which is defined with L of beta, and gamma is another finite state machine, so which is defined by the language L of gamma. So these both are regular. When you perform the union, so we add one more starting state S3 and giving epsilon transitions to these states. So that's what it is defined here. M3 is given by S3 union K1 union K2 sigma delta 3, then similarly S3. So S3 becomes the new starting state. Earlier beta had S1 and gamma had S2. Now the new starting state will be S3, and the accepting states can be either A1 or A2. So similarly this will be using in the construction. So now let us see the concatenation. Okay. So if alpha is the regular expression, beta followed by gamma, then we construct the finite state machine M3, so which is given by K3 sigma delta 3 S3 A3 similarly, and L of alpha is given with L of beta followed by L of gamma. Okay. So this is explained in this figure. See here, this is beta and this is gamma. So you want beta followed by gamma. So this is the concatenation you are forming, whereas alpha is given by beta followed by gamma. So we will connect through epsilon transition. Okay. So here, so alpha is given by beta gamma. So like this, here nothing changes except here you connect the two finite state machines with epsilon. So remember, whenever you want the concatenation, so one after the other, so you should do it. Next will move to the star closure. Okay. Suppose if beta is there, if L of alpha is beta star, then how do we construct? Okay. Suppose here beta is there, so beta star means it is 0 or more number of times repeated. So we'll add one starting state as well as the accepting state to, and with epsilon transitions we'll connect to S1, and from A1 we'll give back to epsilon. That means here this is starting, it can be 0 null, that is epsilon means it is 0 times, so it can be epsilon. So with that it reaches the final state, or this beta can be repeated any number of times. So beta can be repeated any number of times means it is beta star. So we have an algorithm to construct the finite state machine given a regular expression alpha. So this is the algorithm we have, beginning with the primitive sub expressions of alpha and working outwards until an FSM for an alpha has been built. So we will construct an finite state machine as described in the previous theorem. Okay. So next we will consider some of the examples, how to build an FSM from a regular expression. For example, if you have the regular expression B union AB star. Okay. So B union AB whole star. So you observe here, first you need to construct for B, next you should perform AB, then for these two union should be formed, for that whole star. Okay. So let us apply the previous Kleen's theorem. Okay. So it is by construction, this is generates B, this is an FSM for B, and this is an FSM for A, and an FSM for AB will be this one. Okay. So now, so let us move further. So an FSM for B union AB. Okay. So B union B is there, next AB is there, AB, this is the concatenation. Next you want the union. So whenever we want the union, so we add a new state. Okay. So next what you want is B union AB whole star. Okay. So whatever we have constructed B, next AB, next we perform the union, next for this you want the star. Okay. So that means either B or AB, it can be repeated 0 or more number of times. So for that we add an extra start state and accepting state with epsilon transitions, and this is the final figure. Similarly, so for this regular expression, A B followed with A union B followed with B whole star. Okay. So the regular expression will be first B followed with A union B followed with B, and then for that whole star. Okay. So for that whole star means we will add like this, and similarly we will consider one more. So this is the FSM for regular expression BAB followed by A union A star. First B A B concatenation followed with A whole star. Okay. So that means only A star. For this not whole star is there, only A star is there. Either BAB should be there or A star. So either BAB or it is epsilon followed with A star. Next lastly, so this is the finite state machine for A star union B star followed with C star whole star. So this is for a finite state machine for A star, next B star C star. So that is B star followed with C star. Okay. So now we will perform the union. Okay. So this is B star C star followed with star, and for that we will perform the whole star. So if you want whole star means from the accepting state you should connect to the starting state, and another accepting state to the starting state with epsilon transition you should define it. Okay. So these are some of the examples how you can construct the FSM from the regular expression. So let me summarize today whatever we have discussed. Okay. So first definition of regular expression, next coming to the semantic language interpretations. So for the 8 rules, 8 semantic language interpretations we have discussed, and next we have discussed about the how to write the regular expressions for the given language, and lastly writing of, that is the Kleen's theorem first part. For every regular expression there exists an FSM. Okay. So that means normally we will construct an finite state machine with epsilon transitions, as we know that in the module 1 we have seen. So if you have an NDFSM, that is a non-deterministic finite state machine, easily you can convert it into equivalent deterministic finite state machine. Okay. So in the next session, so I will be continuing with the second part of the Kleen's theorem. So thank you all. If you have any queries, you can mail me through this mail ID, that is GIRIJAKASAL@gmail.com. Thank you all.